Schmidt House History Talks. Today's talk is featuring Tim Walsh. Tim is the Chief Hazards Geologist for the Department of Natural Resources for the state of Washington. And he's going to talk about the Ice Age, and particularly its, I guess, how it changed the environment in South Puget Sound. So let's give Tim a very good welcome.
Thanks, Carla. And I'm glad that Carla has an expansive view of history, because I'm actually going to take you back 60 million years. And we're going to have to go through this pretty quickly to get through 60 million years. But mostly I'm going to concentrate on what you see in the first slide, the time when there was ice in South Puget Sound. This is a geologic map of Washington. And the way that we make geologic maps is that we color code all of the geologic units by their age and what kind of rock they are. And the deposits of the last 2.5 million years, what we call Quaternary time, are the ones that are shown in yellow. And you can see that in the greater Olympia area, almost everything is yellow with the exception of some brown rocks that you can see right down here, which mostly are the Black Hills, Tumwater Hill, and Tumwater Falls. The oldest rock in the Olympia area is that stuff. It's the basalt of the Crescent Formation, which is named for exposures at Lake Crescent on the north side of the Olympic Peninsula. But it's very widespread. It goes all the way down to the Columbia River near the Willapa Hills. And these are the rocks that, as you can see, make up Black Hills, Tumwater Hill, and Tumwater Falls. And these were emplaced against the state of Washington by what's called the Kula plate. This is the plate tectonic nomenclature, is that we have plates that are moving relative to one another, and the Crescent Formation was formed on the Kula plate and then plastered onto the continent. This is what that process would have looked like as it was forming. These are submarine basalts that have been photographed by various dives of Alvin, and they end up making pillow basalts like this. And the reason they form something that looks like a pillow is because as it's being squeezed out underwater, it cools very rapidly and it comes out like toothpaste. Makes little globs that then fall into piles. This is what that looks like on the west side of the Black Hills. This is just above Mud Bay. And you can see a number of interesting things. You can see these columns, which form when the lava cools very slowly by conduction rather than convection. That is to say, water's not carrying it away. And the reason it does that is because it makes a big pile of broken up rock that eventually is a large enough pile to insulate what is then intruded into it, and that cools slowly and then shrinks as it does so and makes these columns that you see here. This is a quarry on the backside of the mountains. And then sometime at about 50 million years ago, the ridge that formed the Kula plate was subducted and disappeared. And then the plates had to reorganize themselves, and that created what was called the Farallon plate, what we call the ancient Farallon plate, which was subducted along the western margin of North America gradually. But because its ridge was closer to California than to Washington, the California part subducted first and eventually transformed into the San Andreas Fault, which continues to march to the north toward Washington. But that left a remnant plate called the Juan de Fuca, which I'll get to later. So by the time the Crescent Formation had been plastered against the continent was mostly intact, and then other things happened in place. But Washington is actually a collage of plate tectonic chunks that have been plastered onto it for billions of years. And since this is a talk about the Olympia area, I'm not going to talk about the oldest rocks in Washington, which are about 2 billion years ago in northeast Washington, but just this latest episode. So this is approximately what the shoreline would have looked like once the crescent was in place. And during the Eocene time, and here's the geologic time scale here. So this is what we call the Cenozoic. This is the last 60 million years or so. And Paleocene, then Eocene here. So this is the time period of about 50 million up to about 38 million years ago. And at that time, there were no Cascade Mountains, but there were large rivers that flowed out of the Okanagan Highlands and out of northern Idaho that flowed westward to the Pacific Ocean in a large river system that was probably significantly bigger than the Columbia is today. And it created coal-bearing deposits near the shoreline and then big deltas that fed offshore. We call that the Weaver Plain. This is a diagram of approximately what that would have looked like. So the yellow is the present-day boundaries of Washington, but the shoreline was significantly farther back, probably at about the eastern shore of Puget Sound. And this is what the coal swamps would have looked like at the time. They were hardwood forests, birch, beech, hickory, a lot of plants like that, that would drop a lot of their leaf litter on the floor of these swamps and eventually turn into coal. And is that coming from here? And this is an example of what some of those coal deposits look like. This is the last coal mine to have operated in Washington. This is the Centralia mine. And this is the big dirty coal seam. This is the biggest seam that they were mining. And you can see these enormous trucks down here. These trucks have tires that are as tall as a person. And you can see they're dwarfed by the thickness of that coal seam. And here is the method that they used to mine it. This drag line is a 27 cubic yard shovel that would pull that stuff out. And then this is what the coal mine looked like most recently, just before it shut down a few years ago because of a big landslide that came down from here and covered up the coal that they were planning to mine. And because they had been it had been getting more and more expensive for them to mine coal because they were getting deeper and deeper. That was enough to convince them to stop mining it and then begin to import coal from Wyoming to feed the coal-fired power plant at Centralia. Now, those coal swamps were adjacent to estuaries. They were on deltas. And so there would be these fingers of swamps, but there would be marine waters in between. And these are some of the kinds of critters that lived in those swamps or in those estuaries at the time. This is a snail called a turritella that was a very common critter in the waters at those times. Then at the end of Eocene time, the beginning of what we call Oligocene time, is when the Cascade Mountains began to form, the ancestral Cascade Mountains. And what happened at that time was that there was a large outpouring of volcanic material. Lava flows close to the volcanoes, which are fairly close to where Mount Rainier is today. But a lot of it was very explosive, and it went very far away from the volcanoes as airfall that landed into the ocean. The other thing that happened at that time is that relative sea level rose significantly relative to the time of the coal swamps. All of that was flooded with seawater, and the shoreline moved significantly farther east of where we are now. So a lot of that ash fell into the seawater, settled out slowly as shale, and made deposits like this along the Chehalis River just across the river from Rochester. This is Helsing Junction, and this is a very thick shale, which is to say fine-grained, layered rock that was formed from these ash deposits settling out. And these ash deposits would tend to coalesce around some of the critters that were living there, and they would roll around just like you would make a snowman by rolling snow. Well, some of the critters that were living there would get covered with this. It would roll around, bulk up, and make these round things called concretions, which if you break them open, commonly will have a crab claw or a clam inside. So that was what happened in Oligocene time, and those deposits are well exposed on the west side of the Black Hills and also down around Rochester, and parts south. But we don't see any of that on this side of the Black Hills. By the end of the Oligocene time, when all of those rocks were deposited, that brings us up to Miocene time. And by then, the present-day configuration of the plates was more or less intact. So the Farallon plate was gone. There was just a remnant of it up here that we called the Juan de Fuca plate, and more about that a bit later. So there are no more deposits above the Oligocene until we get to the glacial deposits that are the Quaternary time, which, as you can see here, is the very top of the Cenozoic. This is the last 2.6 million years of geologic time, and the northern hemisphere was plunged into a series of glaciations punctuated by non-glacial episodes that look a lot like what we have today. At least 7 times in Pleistocene times that happened, and the most recent one is the part of Quaternary time that we call the Wisconsin, because these glacial deposits, the glaciers that covered North America, the northern half of North America, are well exposed in Wisconsin, and so we use that as the designation for that time period. So the Wisconsin deposits here in Washington were not the most extensive of the glacial deposits, but they are what's on top, so they're most of what you can see. So a little bit about what a glacial deposit would look like. This is a diagram that shows what the kinds of deposits and landforms are that are left by glaciers. So as this glacial ice that would have looked a lot like that first slide that I showed melts away, it leaves deposits such as these. These are called moraines. So this is the debris that's deposited immediately below or adjacent to the ice sheet. And then as the ice melts back, periodically it might stall, in which case it will dump another pile of this debris, making another moraine. And some of the other things that happen in that process is that under the ice, we get things called drumlins forming that are streamlined hills that are being streamlined by the ice flowing over them. And one of the things about this ice sheet that is different from what you would see in Antarctica is that these are what are called warm glaciers or temperate glaciers. I know that sounds strange, but that's as opposed to polar glaciers or cold glaciers. And a warm glacier is one in which the ice is everywhere at what's called its pressure melting point. You notice that ice floats, and the reason it does that is because it's less dense than liquid water. That is to say, it occupies more space when it freezes. And so if you put pressure on that and drive it back to the liquid phase, that's called pressure melting. So when you have a warm glacier, the ice is everywhere potentially in contact with liquid water. So one of the things that happens because of that is that you can form tunnels on top of, within, or beneath the ice sheet. And deposits that happen within those tunnels are called eskers. And then as the ice retreats, sometimes it leaves stagnant blocks behind, and outwash, the river deposits of melting ice can flow around those blocks of stagnant ice, and when that melts out, it leaves these holes in the ground called kettles. And we'll see some examples of those later on. So the deposits of glaciers are generally called glacial drift, just the general name for anything, but specifically within that, till is the material deposited directly by ice. And if you live on till, as many of us do around here, you'll know that it's very hard to garden because it's, in summer, it gets as hard as concrete. It's an unsorted mixture of clay, silt, sand, and gravel, and it can be very hard. Your water well driller would call it hard pan. So the reason that it's that hard is because it's deposited typically under the ice sheet, and when you have ice that's thousands of feet thick compacting that, it makes it very hard like concrete. And then ice contact deposits are sediments that are deposited against the stagnant ice. And then stratified drift is sediments laid down by glacial meltwater. So those are the deposits, and then the landforms are also important as well. So we already looked at moraines. Those are layers or ridges of till that are deposited as ground moraine, everything under the glacier, lateral moraines or terminal moraines on the sides or in the front of the glaciers. Drumlins we've already talked about, smooth, elongated parallel hills, and they typically occur in clusters that we call drumlin fields. So here are some examples. This is a lateral moraine of the Nisqually Glacier right here. And this is till. You can see it's bouldery and clayey. And then here's another look at the one I'm sitting on, and then across the way as well. And then this is, in Alaska, this is the Matanuska Glacier, and it's retreating. So all of this stuff that you see out here is till that was left behind by it. Here's a drumlin that's just off 41st and Boston Harbor Road, just northeast of Priest Point Park. You can see that nice shape that is much like this classic one in upstate New York. And then landforms made of stratified drift or ice contact, outwash plains. Those are the areas where meltwater deposits sand and gravel that's been entrained within the ice, and typically it makes a braided stream system that broadly deposits sand and gravel out in front of it and makes a plain. And those are typically adjacent to the downstream end of an end moraine. These are often pockmarked with kettles because as the ice retreats, these blocks of stagnant ice might remain behind and get covered with outwash, but then when they melt, it all collapses and forms a pit. And then eskers are the sand and gravel deposited in tunnels on or within a glacier. So this is what's called a LiDAR image. This is a shaded relief image made from laser range finding technology that goes from an airplane flying about 3,000 feet above the terrain, and it sprays these laser pulses tens of thousands of times a second, gets the bounce back from it, and can make a very accurate map of the ground surface. So within this, you can see that the ground here has these elongate hills on it. This is the Key Peninsula. So these are flutes and drumlins. You can see more of them here up above the Nisqually River. And then down here, you can see these nice outwash plains that are areas where just lots and lots of sediment-choked water was coming out of the melted ice. Here's an example of what an outwash plain looks like, again, in Alaska. And then here is all the outwash that is deposited below the Nisqually Glacier. There's the bridge on the highway up to Paradise. And then one other thing that's of interest about glaciers, particularly as they come down valleys, this is the Deming Glacier on Mount Baker. It typically carves these characteristically U-shaped valleys instead of flat-bottomed valleys with steep sides or V-shaped valleys as typical rivers do. So this is an example of an environment in which you might see an esker form. This is a superglacial drainage. So you can see the meandering river on top of this glacier. And here in Alaska, this is the Bartlett Glacier, you can see this tunnel below it with water pouring out of it. So these are the kinds of environments in which eskers form. So again, with a shaded relief image of LiDAR, here's Interstate 5 going through Fort Lewis, and here is an esker that we never would have recognized without this technology. In fact, here I am standing on it, and I wouldn't have recognized it as an esker because the forest is so dense there that I couldn't see from that spot how long and sinuous this thing is. So this is really a wonderful technology for understanding how the Earth works. Here are some examples of kettles. Ward Lake and Hewitt Lake are some of the more prominent kettles in the Olympia area. And then here's the Yelm Highway in between them. At the maximum extent of the last glaciation, And locally, we call its deposits the Vashon Drift. At its maximum extent, the ice made it all the way down to about Tenino, probably about a quarter of a mile north of Tenino. And when that ice filled what is now the Puget Sound, it blocked all of the drainage from going out to the ocean. So all of the drainage coming out of the Cascade Mountains had to flow along the margin of the Vashon Lobe and come around to the south and flow out to the Chehalis. All the drainage from Mount Rainier had to go down that same path, and all of the meltwater coming from this glacier had to go down that same path as well. So a huge volume of water was going out the Chehalis, probably about a Columbia-sized flow going out that river. And that's one of the reasons that it's such a broad floodplain now that has a river that seems not big enough to have made that stream, made that valley. And that's because it used to be a lot bigger than it was. And I'll show a picture of that in just a minute. So when the ice had done that, when it made it all the way to the end and was forming that drainage, it then began to melt back. And we don't have good information on the exact timing of when it melted back. Probably started about 16,450 years ago. Plus or minus 30 or 40. And when that happened, the ice margin was a channel where all that water came out. And then it would melt back a little, and that channel would get wider. And then it would melt back some more, and that channel would get wider still. And in that process, the floodplain deposits going out there would be formed across the floodplain. Then it would be cut down deeper into it and form another one, and so on, having lower and lower terraces formed by this. But these were unpaired terraces because one side of the valley was the block of ice itself. And so what we've shown here is all of the pathways that water sequentially took as the ice was retreating. One of these terraces is littered with boulders. And it was probably littered with boulders because there was a lake impounded in the valley of what is now Carbon River that we call Glacial Lake Carbon. And probably, we think, there was a debris flow that came out of Mount Rainier that temporarily dammed that valley and made this lake. And then eventually the lake and the outflow from it breached that landslide and caused an outburst flood. And that outburst flood carried a lot of the debris coming out of Mount Rainier downstream and deposited a lot of these blocks of Mount Rainier andesite that Pat Pringle likes to call the Stonehenge of Highway 7. And this is the pathway that flood took, all the pink stuff. And the red dots are places where there are piles of these big andesite boulders. And here's some examples of what that looks like. So this is the terrace that was formed by that outburst flood. And a closer look now, you can see all the big boulders that are embedded within these terrace deposits. As you go farther downstream, you can see lots of these boulders everywhere in that terrace edge. And probably we think that they got there by being carried in glacial ice. Boulders that size don't transport very well in water by itself. They would tend to roll along the bottom. But if you have them in glacial ice, they can float and be carried very, very far downstream. And in fact, if you drive out in northern Oregon and go to McMinnville, you'll see a sign for a glacial heritage site up the hill that is a huge boulder like that was carried by one of the Missoula floods and deposited all the way out in western Oregon. This is another LiDAR image. I've colored this one to make it work a little better. Here's Offutt Lake, and here's a line of these kettles. And you can see they're lined up on the outside of the same kind of bend that Offutt Lake makes. And these kettles, we think, were formed by floating icebergs that were plastered along what would be the cut bank side of the river flowing through there. And then they deposited the bergs there, they melted out and formed all of these kettles, most of which are dry here, except for Offutt Lake. And here's how bouldery Offutt Lake is. This is its south shoreline. And you have to take my word for it because I didn't put a compass on this, but these crossbeds that you see here are aiming downstream, and that downstream is to the southwest toward the Chehalis. So that's further evidence that all of this was flowing out to the Chehalis, or more specifically, at this point, to a lake that was formed in the Chehalis Valley that Bretz called the Chehalis Bottoms. And as that process was carrying on, these river channels wouldn't always just extend all the way across the area between the ice sheet and whatever the hills were to the south. They would cut channels through in various places. So you can see in this shaded relief map, here's Spurgeon Creek that cuts into this upland here. Here's the Deschutes coming through here, and it used to go, you can see all these kettles again here, so the Deschutes came down through here and out this pathway until the ice was far enough to the north that it exposed what is now Puget Sound. So once the ice retreated past the points, Cooper Point, Steamboat Island Peninsula and the like, then that began to form a lake, and the Deschutes River was able to find its way into this lake that we call Glacial Lake Russell. More on that in a second. So these ice marginal terraces, we call them, are the places where Mima mounds are concentrated. All of the Mima mounds in western Washington are located on one of these terraces that was formed by water flowing out to the Chehalis, as opposed to on any of the outwash plains that were formed by meltwater coming directly out of the ice. This is what one of those Mima mounds looks like. My agency cut into this about 3 years ago and exposed the gravel underneath and the black, finer grained soil that makes up the mound itself. And the reason for the blackness is that when about 5,000 or 6,000 years ago, when forests, when the climate warmed up enough that forests began to encroach on the prairies of South Puget Sound, the Indians would burn the prairies for a couple of reasons. One is to make camas bloom, and the other is to keep the forests down that were encroaching on the prairies where they lived. So the blackness of this is actually soot from that soil burning. Here's another example of these Mima mounds that form in these big clusters. This is the Mima Mounds Natural Area Preserve on Delphi Road. To go look at this, you need a Discover Pass, though. And here is another air photo of them. And you can see that they're not round. Some of them are round, but some of them are very elongate. And so that gives rise to one of the theories for how they formed. Colonial gopher mounds is one of them. But another is that they were patterned ground that then had meltwater flowing around them that eroded the edges of the patterns, and I'll show you what pattern ground looks like in a second, and eroded them. And this streamlining is a matter of the direction that the water was flowing to carve them. And then earthquake-induced mounds is another idea that has been raised for them, that if you, and this was the experiment that a guy named Dave Berg did, if you take a sheet of plywood and cover it with sand and then tap it with a hammer, what that'll do is cause seismic waves to pass through it, and the sand will migrate away from the nodes and toward antinodes where it's not shaking as much. And so you'll tend to form mounds in the antinodes of the shaking, and that'll be moving away from the nodes. That's probably not what's going on here. So these are some examples of polygons in nature. So here are columnar basalts that form that way because as they cool slowly, they shrink, and they make these polygonal shrinkage cracks. Permafrost does the same thing. and mudflats do a similar thing. So the permafrost is one of the ideas that was suggested by Link Washburn, that what happened is that you would have these areas of permafrost, and then when the water flowed around, it would enlarge the cracks between them and form what we now see as the Mima Mounds. J. Harlan Bretz, one of the pioneering geologists out here, and I'll show more of him in a minute, suggested, and Josh Logan and I worked on this together about 4 years ago. Josh really liked this idea, that the mounds formed in what are called sun cups. If you've ever been skiing on a bright sunny day, you'll see that there are these pits in the snow surface that accumulate liquid water. And they're called sun cups. And as they form and as they accumulate liquid water, they attract more and more sunlight, warm up more and more, and so they enlarge into these cups. So what Bretz and Josh like to think is that what happened as these prairies were forming, as the ice retreated, it retained some permafrost for several years. And then when these floods would come through, when summer arrived, and you would have more meltwater coming off the glacier, and so you would get these bigger floods, that the flood waters would carry silt that would deposit into these sun cups, make them darker, make them attract more sunlight, warm up some more, and eventually fill up with sediment. And this is an example of what these sun cups look like. Well, once the ice had retreated, again, all the way past these points here, that impounded a lake called Glacial Lake Russell. At that point, all of the streams that had been flowing around the ice and out to the Chehalis reorganized and began to flow into Glacial Lake Russell. But all that water had to go somewhere, so it spilled out along Percival Creek, along the railroad tracks there now, went down there into Black Lake, and then it flowed out the south of Black Lake along the Black River and into the Chehalis that way. And so all of the meltwater then had to go down that pathway. And that's why the Black River is such an underfit stream, because it used to also carry a Columbia-sized load of water, but now it has only a very sluggish amount of water in it. And so if you've ever tried canoeing it, you'll find that you might get stuck in places for quite a long time. Now, when these streams were flowing into Glacial Lake Russell, the elevation of the lake was controlled by the spillway out Percival Creek, and that's at about 145 feet above sea level. So the rivers were flowing into this lake, whose surface was 145 feet, and it was very deep, therefore. And so gravel deposits from these streams would dump down these slopes like this and deposit deltaic sand and gravel that would be hundreds of feet thick. And these are some of the most important gravel sources, all of these deltas into Glacial Lake Russell, because you can get a lot of gravel in a small area because the deposits are so thick. So this one is DuPont, and this one is the Holroyd mine known as the Sherwood Delta out along the right bank of the Nisqually River. So that was the flooding stuff that happened in western Washington, but at about the same time there were big floods happening in eastern Washington. And this gentleman, J. Harlan Bretz, was the person who figured this out in the first place. So you can see this black dotted line is showing where the ice came down in various places. So we've been talking about the Puget Lobe here. The Juan de Fuca Lobe went out there, but there was also ice in the Okanagan and Columbia lobes, and then more importantly for this story, the Purcell Lobe. So as ice flowed across these passes here, and particularly the Clark Fork River, it impounded a lake behind it that we call Glacial Lake Missoula. And the water would rise up until the water level was high enough to float the ice dam that had made it in the first place. And somebody asked about yokel-ups. So that's what a yokel-up is. It occurs when an ice dam floats and the lake behind it debouches into the valley below. So this is where glacial Lake Missoula was. You can see it occupies a lot of northwest Montana. There was also a glacial Lake Columbia that was up the Sandpoil River Valley. And then when these Yoakuleps happened, the floodwaters came across the Columbia Basin, down through the Columbia Gorge, flooded the Willamette Valley, and then went out to sea. And that's, somebody was mentioning having seen the glacial erratic at McMinnville. This is the process that brought it there. And as the floodwaters cut across the Columbia Basin, it cut into the basalts that were deposited out there and made these steep-walled channels called coulees. And in places, it brought those together in waterfalls because the basalt is columnar. And so what would happen as the water passes through is it would peel off these columns, and you would get headward erosion, and very steep headward erosion at that. So this is an example of the biggest waterfall that formed that way, Dry Falls at the south end of Grand Coulee. You can see these big columns that are what peeled off. Now, when that water got to Wallula Gap to go down the Columbia Gorge, more water was coming down than could pass through the gorge. And so it backed up, a process called hydraulic damming, up into the Walla Walla Valley. And when that happened, the waters would flow up valley, deposit sand, and then when that would fill the valley and go to still stand, then silt and clay would settle down on top of that. And each one of those floods would make one of these sets of sand and silt. You can see that close up over here as well. So here in Burlingame Canyon, there are 43 such sets of fining upward sequences of sand through clay that are interpreted as either individual floods or individual surges from a given flood. So Richard Waite thinks that there were 43 separate floods. Gary Smith thinks it's only 13 that had multiple pulses, but nonetheless, it's evidence of quite a lot of flooding. Now, we've had glaciers occupying South Puget Sound multiple times throughout the Quaternary. Each time that happens, though, it deranges the topography and the landscape in general and destroys a lot of what was previously there. So it's difficult to piece together what the landscape of South Puget Sound looked like. And in between each of these glaciations, we would have a non-glacial period, like what we're in right now. But because the landscape was deranged, it didn't look the same way in previous non-glacials as it does today. So I'm going to show you outcrops here at Butterball Cove along Nisqually Reach near the Nisqually Delta over here, and something over here at the south end of Ketron Island. And I'm going to make reference to this point number 6 on Anderson Island. So this is Butterball Cove. What this white sand is pumice, broken pumice from Mount St. Helens, or from a volcano that used to exist near where Mount St. Helens is today. And this is ancestral Nisqually River deposits, black andesites that come down from Mount Rainier because the Nisqually rises on Mount Rainier. And this is just a few feet above sea level, and you can see that on Anderson Island, these same deposits at the same elevation. So what that tells us is that at the time of this deposit, which is about 100,000 years ago, there was no Nisqually Reach. The Nisqually was able to flow all the way across it out to Anderson Island and beyond. This one below is from Ketron Island, but it's at an elevation about 75 feet above sea level. This one comes from Mount Rainier. These little pebbles that you see here are pumice fragments that floated down with a flood that came out of Mount Rainier about 162,000 years ago. This was the Sunset Amphitheater pumice that makes up this deposit. And because it's about 75 feet above sea level, what that tells you is that not only was Nisqually Reach not there, but the shoreline was all the way up to Tacoma because the river, the Nisqually River, was grading that far to the north. So this sequence of glacial and non-glacial deposits controls hazards as well as resources, and the landslide hazards are a function of this. So just quickly, the way a landslide works, and the simplest way to look at it, is that the forces acting on a hill are just gravity. So on this rock, gravity is acting straight down. But if you tilt this surface up, gravity is still acting straight down, but it has a component along the slope and a component perpendicular to the slope. And this is the driving force, and this, plus the frictional coefficient of this thing, is the resisting force. So you get landslides when the driving force exceeds the resisting force. And this is an example of what that looks like along Puget Sound, that we have till on top of sand and advanced outwash, sand and gravel, and then a clay beneath that. That's specifically, Seattle has rocks that we call that, or dirts that we call that. But we have that kind of a sequence everywhere. So these clay deposits are relatively impermeable. Groundwater percolates down to it and can't go any further. So it builds up pore pressure in these overlying sands and gravels. And so it doesn't actually increase the driving force, but it decreases the resisting force by making it relatively weaker. And so in this kind of a situation, heavy rainfall tends to create a lot of landslides because it builds up high pore pressure in these overriding porous and permeable sands. Here's an example of one of those that happened on December 3rd of 2007 following that big storm that I imagine most of you remember. So here, way back up here, that caused a slump, a little landslide that came out of there and landed in the stream. It then bulked up, picked up some water, became loose, and flowed down the stream, picked up more sediment as it went downstream, and went through the Ranch House Barbecue down below and pushed it 100 feet off its foundation and all the way out onto Highway 8. So that's one of the consequences of the kinds of geology that we have here for our slope stability issues. And then I'm going to finish up talking about the earthquake hazard here. I hope all of you remembered to drop, cover, and hold at 10:17 this morning for the great shakeout. No. Nope. Oh well. But at any rate, Washington has a high exposure to earthquakes. We've had at least 15 damaging events since 1872, and not always on the west side. That 1872 event was over near the town of Chelan. And geologic evidence demonstrates that we have hazards from faults that haven't ruptured since European settlement. And we've got a whole bunch of those that we've identified: Seattle, Tacoma, Southern Whidbey Island, Devil's Mountain, Canyon River, Boulder Creek, Toppenish Ridge, and Saddle Mountain faults. All of those are capable of making earthquakes bigger than about a 6.5. And then additionally, we have significant evidence that the Cascadia subduction zone is active and has made big earthquakes. This is what the overall tectonic setting looks like today. Here's the Juan de Fuca Ridge that's making new seafloor crust that's pushing under the North American continent in what is called the Cascadia subduction zone. Big earthquakes can happen at that interface, but also as the subducting slab gets pulled into the mantle, it gets pulled apart. And so within the slab itself, you can have earthquakes that are called Wadati-Benioff zone or just Benioff zone earthquakes that are like the earthquake we had in 2001. And then we also have faults in the upper crust that I've identified a bunch of them here that also are potential seismic sources. So the orange earthquakes here are earthquakes that are in the Juan de Fuca crust, the subducting slab. And the green are earthquakes that are in the overriding North American plate. So this is a cartoon of what that looks like these earthquakes that are within the subducting slab, these Benioff zone events, typically happen at depths of about 45 to 60 kilometers. And these are the ones that are most common around here. I suspect many of you have experienced more than one of these around here. This one is 1949, April 13th, magnitude 7.1 it was called at the time. Today we would call it a 6.8, using a slightly different way of scaling it. Then in 1965, another one. This one in 49 was located under the Nisqually Delta. This one was located under SeaTac. And then in 2001, the Nisqually earthquake, again located in about the same place as this 1949 event. And there was a lot of building damage around here, but some interesting things, and I'll swing back around this a minute later, is that this earthquake caused Cooper Point, the northern 200 feet of it, to disappear into the water. And here's a close-up of that. So there were a couple of fishermen who were out there, and they didn't feel the earthquake because earthquake waves don't transmit through water. So they were just fishing, not knowing that an earthquake was happening, and the northern tip of Cooper Point disappeared. Here's some examples of the kind of damage that does to buildings. So this is the Dries building from the 1949 earthquake, and then down the street from it is the Washington Fed building from the Nisqually earthquake. And in Pioneer Square, here's the 1949 earthquake damage and the 2001. And note that what typically happens is that weak unreinforced masonry parapets collapse onto the street. We fix these after they happen, but we haven't gone in and fixed them before this happens the next time. But it keeps happening over and over. Liquefaction and landslides also happen during earthquakes. When liquefaction happens, the water-laden sand becomes loose. The pore pressures build up, push grains apart, and then the load is carried by the water itself. And that causes it to be very weak and slide on very low surfaces, such as happened along Deschutes Parkway here in 1965, and again in 2001. And the only reason it didn't happen there in the 1949 earthquake is that this road was built in 1951. Here in Tacoma Narrows, the 1949 earthquake generated this big landslide that went into deep water and generated a tsunami that was about 8 feet high at Gig Harbor and then reflected back across to drown these houses. And those of you who have gone to some of the Henderson House history talks have probably heard my colleague Weldon Rao give some discussions of geology around here. Weldon was at UPS at the time of the 1949 earthquake, and the State Patrol noted that there were cracks in the ground, so they asked Weldon to go out and look at it. And Weldon walked it out and saw that the cracks went all the way out here, so he recommended that they evacuate these houses, which they did. And then the wave reflected back and drowned all of those houses 3 feet deep. Now in 2001, the rest of this landslide scarp right here failed into those houses and severely damaged them. The next kind of earthquake is these great subduction zone earthquakes. Worldwide, these are the biggest earthquakes. They get up to a maximum magnitude of 9.5 that's ever been recorded. And we haven't seen one of these in historic times in Washington. But the reason we know they exist has to do with geologic evidence. So the biggest of these happened in 1960 in southern Chile. The area within this band sank 2 meters, or about 6 feet, and the area out closer to the fault uplifted about 6 meters. So in the area of subsidence, and focus on these trees for reference, the ground subsided here 6 feet, and it was followed by a 30-foot tsunami that completely removed the town. Here are those trees again for reference. And the reason the river is wider here and there's a lot of floodwaters left is because the ground is 6 feet lower than it was before the earthquake. Same thing in Alaska. The ground subsided 2 meters in here, uplifted as much as 10 meters out here. And this is what that looks like. So here is a drowned forest that was an upland forest about 45 miles east of Anchorage, sank 6 feet and was washed over with salt water and killed. And here is a similar forest along the Copalis River that was killed by one of these events in AD 1700. When the ground subsides near the shoreline moves inland. So in Turnagain Arm, the shoreline moved in about 6 kilometers, eroded the channel bars within the rivers. There's a 30-foot tidal range here, so that redeposited sediment on top of that 1964 surface right here as the Placer River silt. And down here, we see along the Neowayakam River, which is a stream into Willapa Bay, a similar buried soil overlain by silt, and then an older one, still older, about 1,100 years old, this buried soil overlain by silt. So what actually is happening here is that between events, when the ground is stuck, it's still moving closer to one another, so the ground has to bulge up. But when the earthquake happens, that bulge collapses, and this shortened area extends up the rupture plain. And that process also creates tsunamis, as we can see here. Here's the AD 1700 ground surface, the silt on top of it, but a bunch of streaks of sand that were deposited by several tsunami waves that came in after that. And then finally, the upper crust can have earthquakes like the ones we see in California. These are all of the areas that we think we have these active faults. And here's a close-up of that. So we have the Darrington Devils Mountain Fault, Utsaleti Point, Southern Whidbey Island, Seattle, Tacoma, and Olympia faults. And here's an example of why we think we have an Olympia fault. This is gravity. Believe it or not, gravity is not a constant because it's also affected by the mass of material between the Earth's surface and the center of the Earth. So where there are denser rocks, gravity is higher. Where there are less dense rock, gravity is lower. And what we can see here is very dense rock with an abrupt edge to much, much less dense dirt. And we can also see in magnetics the same sort of thing in approximately the same place. This is Red Creek on the Nisqually Delta on the Pierce County side. And note all of these tree roots that are sticking out here. This is looking along where the next slide is going to be in this block right here. And what you can see at this site, you can see here these little streaks of sand. That's this right here. And there's another one there. And that erupted into a sand volcano, vented sand up here, that happened because of liquefaction. The ground shook hard enough that liquefaction happened, squirted it up to the ground surface, and deposited it here. And that was about 1,000 years ago. So back to the Cooper Point landslide. So there's some seismic reflection profiling that was done by some people at UW. Here is the Cooper Point Peninsula, and they think they've identified a fault going right through there, right across the northern tip of Cooper Point. And here you can see in the seismic the disruption that happens at that location. So it's possible that that landslide was actually the fault moving. And then finally, up in the Skokomish Delta at the Great Bend of Hood Canal, you can see this ridge cutting across the delta and forcing the river over here. Here's a closer look. This ridge causes the river to be out here, and so the river comes out only in the southeasternmost part of the delta. There's no water that makes it out over here. And this is what the ground looks like where that ridge is attached. The sediments that these guys are looking at are dipping steeply in that direction. And there you can see them again. And that's what's at the head of this ridge. So we think that this is probably indicative of a fault that's buried and is causing folding above it. And because the best evidence for it is behind that sign, we call this the lucky dog structure. And in aeromag and gravity, you can see that there are structures that occur across there as well. Still working on it. Thanks.
Are any of those maps or LiDAR images available to the public or on your website or anything?
Yes-ish. Which ones? I showed lots of maps and LiDAR images.
Well, of course, I'd like to look in the area where I live, and because we're in the old Black River.
Well, now I've done some processing to those LiDAR images on my computer using ArcGIS, which costs thousands of dollars, so I suspect many of you don't have access to it. But you can get images that are similar to that on the Puget Sound LiDAR Consortium website. I can't tell you exactly what its address is off the top of my head, but just Google Puget Sound LiDAR Consortium, and that will lead you into a place where you have to register, but it's free. They just want to track who's using it. And once you register, it'll take about an hour before it populates well enough that you can get into it. But you can go there and look at these shaded relief images of a lot of the areas that have LiDAR. So you could look that up where you live if it's been flown. There isn't LiDAR everywhere.
How do you spell LiDAR?
LIDAR. And it's an acronym that stands for Light Detection and Ranging.
Is that done all over the Southeast Tim?
We have LiDAR for most of the Puget Lowland, most of the Chehalis Basin, most of the Strait of Juan de Fuca out to about Clallam Bay. And as we speak, we have a mission going that is from La Push up to Cape Flattery.
Do you have any pertaining to the Issaquah area?
Yes. King County is completely done, although the quality of the LiDAR there is fairly poor.
That figures.
Well, part of the one of the issues is, and I didn't explain this, but the LiDAR instrument, when it shoots the pulses, it puts a GPS timestamp on every pulse. And then it has 4 receivers, so a pulse can go down, hit the top of a tree, hit the middle of a tree, hit the top of a shrub, and hit the ground. And you can separate out all 4 of those because you have 4 receivers, and you can identify them as being the same pulse because they're GPS timestamped. So that allows you to separate out those first 3 returns and concentrate on the last one, the one that's most likely to be a ground return. Well, the problem with a lot of the King County LiDAR is that it was flown in summer. And we generally try to fly LiDAR in winter so that we have leaf off, because it's easy enough to model Doug firs, but it's a lot harder to model and to penetrate through alders and maples and the various hardwoods that you would have out there. So because they flew it in summer, it doesn't have as good a ground penetration.
I'm concerned about our lack of preparation for the next subduction zone earthquake. Can you say briefly how bad it's going to be afterwards, what we're facing?
Go to the website, crew.org. We just released on Monday a scenario of a Cascadia subduction zone earthquake that's been updated. Released it on Monday to coincide with the Great Washington Shakeout this morning.